So we know the capacitor's charging curve look like this. How do the discharging curves look like? Also curvy, curvy. Yeah, but the charge is actually decreasing. But in what manner? Let's say you start off with a certain Q naught. Q0 is Q naught lah. Okay, so you discharge the capacitor. Discharge Q will then zoop, decrease and reach some point. Okay. Consequently, also the PD across the capacitor will also decrease in the same manner. Okay, so from a certain initial voltage, it will decrease pretty much to almost zero. Current though, when you are discharging a capacitor, it is actually the same as whether you are charging or discharging. So the moment you connect the ends of a capacitor, the charge is like, yes, we are free. They flow really large with a very large initial current, but that current will slowly decrease and everybody go back to the original position. Then they're like, yeah, okay lah, we slowly. So it's very strange, huh? All of it being drawn like this. The question is, why are these graphs shaped this way? Why not straight line? Why curve like that? Why not curve the other way? That is the answer that we're going to look for today. So the answer is there is some maths involved. So a warning, if you are not taking A-level maths, don't worry, you can just enjoy the maths. Or if you do, then you will see hopefully a useful application of maths. So let us rewind to the circuit that we're looking at. So if we have a normal circuit, like we have a battery with some EMF, okay, and it's connected to a capacitor, make sure the lines are equal, and connect it to a resistor to slow down the discharging or charging process a little bit. So your battery, I'm just going to use VB here, voltage of the battery. This is resistance R, this has capacitance C. Now you're going to have some current that flows through like this, current I, and you will have a potential difference across this capacitor that will be changing lah, V. Let's call it V for now. All right. So if we use Kirchoff's second law, Mr. Kirchoff's second law, to come up with the equation to start us off, we get this. So the first step is to think about this. Okay, Kirchoff's law says EMF rise equals to EMF drop. So that means the voltage across the battery, VB, must be equal to the potential drop across the capacitor and also the potential drop across the resistor. Okay, you rise this much, you go down. No. Okay, usually we say EMF lah. For now, we'll say voltage of battery. Now here, you can expand this equation a little bit already. So voltage of battery, I'm just going to write VB for now, equals to voltage of capacitor. Oh, remember Q equals to CV? So V is going to be Q over C. So the charge at the capacitor divided by its capacitance. That will be the voltage across the capacitor. Let's call this VC for now. Then the last one, VR. We can use our good Ohm's law. V equals to IR, current flowing through the resistor times its resistance. We do this because we know R, and I will be useful later. The next step is where it gets a little interesting. We are trying to find an equation for this graph. We need Q against T. Somehow, we need to get that out from this equation right here. How do we get a equation for Q against T? Think a little bit. There's Q there, but where does the T come from? Do you see it? So if you look very carefully, this VB is still a constant, voltage of battery. Q over C is pretty much a constant, but I, current, can be defined as dQ dt times R. Just put the dQ dt there. Okay, so the rate of change of rate of flow of charge over time is dQ dt, and that is defined as current. That's the definition of current lah, okay? So if you recognize this, you recognize that it's a differential equation of the first order. Let's rearrange. So you have dQ dt, usually we write it like this, R dQ dt plus 1 over C is just a constant, but Q is what we are looking at because Q is on our y-axis. Then the VB, we also move to be on the same side. So that would be VB over there equals to 0. Recognize this. How to solve? Well, if we can find a general solution of this equation, that will give us a head start. So generally for equations with this pattern, I got dq dt something plus q something something constant. There is a general equation, or what we call the general solution. So the general solution for this is it's going to be looking something like this. An equation where q equals to some constant a times exponential negative kt. K is some constant. I don't know why it is. I just put constant first. Okay, b is also a constant. This here, q, is your charge on your capacitor. So we are kind of done. Hey miss, but this one, I'm not very satisfied. Okay lah. This is just a general solution. Now we need to come with a specific solution. So we're going to proceed with this general solution. Q against T, but for, let's start with discharging first. We won't have enough time to do everything, but discharging. Okay. So whenever you have a general solution, you need to plug in your initial conditions and final conditions of your system, what is happening to the capacitor. So if you want to plug in for discharging, where to write? Here lah, discharging. What happens at the beginning? What is the initial state? So at t0 at the beginning, if you look at the graph, you have some initial charge, right? Right. The initial charge is Q0. You look at the graph, the intercept, Q0 right here. So that's one condition, but maybe I have an idea. That one might be a little bit harder. We might not have enough information for that. So let's say the final condition. At the end lah, okay, as t is very, very far away, approaching infinity now. You are looking at this tail end. What happens after a very long time? There should be no more charge. It should be about 0 lah. Okay, so Q should be 0, fully discharged. I like that 0 thing. So Q is 0. So what we're going to do is we are going to sub that into our general solution on the top right. What do we get? Okay, so for this first step, if we sub in Q0 equals to A e to the infinity, okay, negative infinity or infinity, either one, plus B. E to the infinity is what? You press calculator for a very, very big number. E to the power of a negative number, very big number, is going to be 0. You don't believe me? You take calculator, you press e to the power of negative 999999999. It will be 0. Okay, so that's going to be gone. This whole thing is gone. So A times 0, 0, A times 0 plus B. So that tells me that B is 0. Oh, so the general solution, no need to write B also can lah, because B is 0 for this condition, final condition. But also, we need to use another condition for in the beginning. So at t equals 0, this is the one we do this now. So Q will have some initial charge, Q0. Beginning you have some charge stored there, then you discharge now, no more at the end. So we're going to do the same thing, sub into our general solution. So now B is gone, but let's just write it out. So Q0 equals to A E negative 0 plus, what is B? Oh, B just now 0. So many 0, I like it. So 0 is gone. E to the power of 0 is what? Press calculator if you're not sure. E to the power of 0 is 1. So all you have left is just Q equals to A. That's it. Oh, so we have found our constants. Our constants being A, B, miss, how about the K? Now the K thing, people have to kind of do a little experiment. How do people figure out the constant K? I will tell you the shortcut. K is actually 1 over RC. Wow, miss, what is this? Okay, right here. K equals to 1 over RC. RC is also known as the time constant. Time constant, we use a symbol tau. but never mind about it. So time constant tau is 1 over RC. But what is a time constant? So people have defined time constant of exponential decay. This is what we call exponential decay. Time constant is a time taken. So this is 1 tau. Tau looks very weird. 1 RC. Okay, this is RC. So after 1 RC, your charge Q would have decayed to about 37% of its original value. That is how we define it. So 1 time constant later, you decay to 37% of original value. 2 time constant later, decay some more. Okay, where did 37% come from? E to the power of -1. This is where your 37% or 36 point something percent comes from. Okay, so essentially we are saying, oh, if you have this e to the -1 times q0, you should get your q. Okay, so that is what we are looking at lah, where the time constant comes from. But don't worry about where it comes from, just know what is a time constant. Tau equals to RC. So I put a little comment here. Tau is RC, time constant. So put all these things together, we have a pretty complete solution for our charge. So let's do this. C. Let us now sub all constants into our general solution. So we will have something like Q equals to A is what? Q naught. Okay. Then E negative K. Yeah, this one just put negative T over RC. Plus B. Got B? No B. So that is it. Okay. So this tells me that the equation for charge, especially discharging, is going to be an exponential graph with a -1. So you flip the exponential graph. So that is actually talking about this shape. So that is saying, hey, this graph is actually Q equals to Q naught E negative T over RC. This is why the graph is shaped that way. It's an exponential decay. And there are properties that we can tell about it, such as the time constant and things like that. From there, how do we get the V and the I graph? Well, for the, let's do the V graph first. So if we want to find the voltage across a capacitor, how does V and Q relate? You think about it. Can you remember? Q equals to CV. So if you have certain charge across a capacitor and you have a certain capacitance, then you can find the voltage across the capacitor. But we want to find V, right? So V equals to Q over C. Q, we already know, it's right here. So the Q is changing over time. After a long time, got a lot of charge, or lesser charge since we're discharging. So we can say 1 over C times the whole Q, which is Q naught E negative T over RC. Okay, so we combine that. Q naught over C, original charge over C. That is also known as the battery voltage times E negative T over RC. Also known as the original voltage of the capacitor. How do I know it's this? Well, show you in a bit. But this is how you find the equation for that. So also an exponential decay going down. Okay, so if you are wondering why is it voltage of battery, when your capacitor is fully charged, remember, you will reach the battery voltage. So you start off with a battery voltage and then you decrease down to 0. That's why VB here is Q over C. Q naught over C. Okay, last one. Okay, we found voltage, also exponential decay, so you can also write this. V equals to V naught or VB E negative T over RC. That is this one. The last one, current can find. This one is a little bit more tricky, but yes, we can find it. Same method. How to find current from I or Q? Some people say, Miss, V equals to IR. There's no R of capacitance. Well, Not exactly, but there's no RR. We can't use V equals IR. But there's another way we can find current through the capacitor and how it changes over time. That is through I equals to dq dt. Oh, rate of change of charge at the capacitor. But this is discharging, so there's a negative here. Discharging. So if we want to differentiate this, miss, have to differentiate. Yeah lah. So we go and differentiate lah. So I equals to negative of, you differentiate with respect to time, Q naught E negative T over RC. Man, this is getting a bit small. I'm going to zoom in a bit. So what we have here will be negative. How do you remember how to differentiate? This thing, oops, kind of highlighted too many things. This component will come out. So we have negative T over RC multiplied by Q naught E negative T over RC. So what we get in the end will be T over RC Q naught E negative T over RC. Wow, very messy this equation. Can simplify a bit. Hey, I just realized a mistake. This one, the T, what is the T doing here? Hello, T is not supposed to come out. It's just 1 over RC, 1 over RC. Okay, there are ways to simplify based on this. Q over C. Does it ring any bell? Oh, wait, Q equals to CV. So Q over C equals to V. But what V is this? This is the voltage of a battery, or the initial voltage of the capacitor. So this one will be VB over R times E negative T over RC. It not look very nice. Can simplify some more. Can. You can simplify V over R. That looks familiar. V equals to IR. The R here refers to the resistance of the resistor. That's the only one that has R. That's where the R comes from in the first place. Okay, so V over R will be I. So you can say, oh, this is the initial current flowing through the capacitor. Ta-da! And you have your equation for this one. So this is how you can find the current through the capacitor, the voltage across the capacitor. I didn't highlight this. Never mind. And of course, very importantly, the charge at the capacitor at any point in time with respect to time. So let's label this graph here as well. So this one, I equals to I naught times E negative T over RC. Okay. Now, if you're curious to figure out more, I encourage you to try out the derivation for charging and discharging. See if you can get the curves. But if you are wondering what is the equation for the curve, for this one, there's also an exponential. It's a little bit different. For that one, the exponential charging curve is Q equals to Q naught. No more miss. No Q naught. You start off at 0. So this one, the equation is a little bit different. This is Q naught 1 minus E negative T over RC. Can you derive this with the method? Try it out if you know or you have learned this in maths. For this one, also very similar. This curve is V equals to VB, which is that VB battery over there, 1 minus E negative T over RC. So what gives this curve its shape is the 1 minus E to the power of negative T. That is the one that gives it that increasing and then flatten out kind of shape. So you end up at a final charge, and that is. So go try it out, see if you can derive these two equations for charging and discharging of capacitors. Okay, so that's all for this one. Where the graphs come from, and very importantly, what is a time constant? Tau is time constant, which is RC. It's a property of an exponential curve, either charging or discharging lah. Okay, so that's all for this additional video about the maths behind charging and discharging. Hope that you found that helpful or interesting to learn about in applying your maths understanding. Okay, so that's all for this video. We shall continue on learning about capacitor in the next video.